In this video, we're going to be talking about the methods of analysis for quantitative data. So what are quantitative data? Quantitative data are numerical representations of our observations in the social world. What that really means is we're attaching numbers to something we see in social life. And what we're trying to do is essentially both describe and explain what's going on in the social world. And instead of pulling out meaning or experiences like qualitative data would do, quantitative data instead convert those to numbers. Whereas in qualitative data, you talk to someone or read the text of an interview or read the text of a biography and try to pinpoint themes that are popping out. On the quantitative side, you can also look at themes that are popping out in someone's text, but instead of saying they said social ties were important, you say, did they say that social ties are important? Yes or no? And instead of saying yes or no, you give that a number. 1. Or how many times did they say social ties were important? We see that they said something about social ties 10 times. So we can attach numbers to those same kind of raw data, converting it to a quantitative form. The actual process of coding in quantitative methods is assigning numbers to various attributes of the variables that we're looking at. So we can look at variables such as age or sex or political affiliation or socioeconomic status and see that we can attach numbers to those things. For example, if we look at age, we can measure it as somebody says they're 1 year old. Someone's 2 years old, they say they're 2, 3 years old, 3, so on and so forth. Because we're dealing with interval ratio level variables or variables that have numbers assigned to them, we may want to group those numbers into larger categories, those attributes into larger categories. So we can say anybody less than 18, they get a 1. Between 18 and 24, they get a 2. 25 to 29 gets a 3. 30 and plus gets a 4. Either way, in the above version, where we're attaching the exact number to the exact age, or here the below version where we're attaching a number to a grouping of ages, either way the outcome is the same. The result is we've assigned numbers to the right hand column. Sex. Instead of saying male, female, other, we can assign numbers to those categories, those attributes. Female equals 1, male equals 2, other equals 3. We could even do a dichotomous variable or a binary variable, a series of binary variables. Instead of saying female equals 1, male equals 2, other equals 3, we can create a variable called female. So instead of calling the variable sex and having 3 attributes, we can create a variable where the attributes are yes or no, 0 or 1. So does somebody identify as female? Yes or no. Then we create another variable called male. So now instead of one variable sex with 3 attributes, we have one variable female with 2 attributes, yes or no, 0 1. The next variable male with 2 attributes, yes or no, 0 1. And then we have an other and say, do you identify as other, yes or no, 0 1. Like I said before, it's called a dichotomous variable or a binary variable. It's called dichotomous or binary because of 2. You have 2 options, yes or no. Converted to numbers, yes usually equals 1, no usually equals 0. When we're creating dichotomous variables or binary variables like this, we create a certain number of variables. The number of variables that we create is k minus 1 number of variables. So again, we have the sex variable. Let's say that k here, k minus 1, is the number of attributes, right? So we have one variable with 3 attributes. So if we wanted to convert these to a series of dichotomous variables, we'd say k attributes is 3, k minus 1 is 2. So we would create 2 new variables. Instead of one variable sex with 3 attributes, we'd have one variable called female with 2 attributes, yes, no, 0, 1, and another variable called male with 2 attributes, yes, no, 0, 1. Why don't we need to make a third category? Why do we say k minus 1? The number of variables that we're making is going to be equal to k minus 1, the number of attributes in that first variable minus 1. Why do we do that? Well, let's assume somebody identified as other. When we make 2 variables, somebody who identifies as other, how would they be identified across these 2 variables? We could identify them by if they get 0 on female and 0 on male. This idea of k minus 1 for creating dichotomous variables based out of larger variables is based on mutual exclusivity. If you get a 1 here, you are automatically excluded from the male variable and the other variable. If you get a 0 on female and a 0 on male, that means you don't identify as female or male, but that means you identify as something else. So that would be other. So the concept of mutual exclusivity is important when it comes to these series of dichotomous variables. Let's take this idea of political affiliation next. We have one variable with 4 attributes. If we wanted to create a series of dichotomous variables, how many would we need? We would need k, the number of attributes, minus 1 number of variables total, right? So K, here we have Democrat, Republican, Independent, Other. We'd have 4 attributes, meaning we would need K minus 1. 4 minus 1 is 3. We would need 3 new variables. What would they look like? Democrat, yes or no. Republican, yes or no. Independent, yes or no. And then we're good, because anybody who got 0 on Democrat, 0 on Republican, 0 on Independent, they'd automatically be assumed that they have a 1 on the other category. So with political affiliation, we can assign numbers. These numbers don't mean anything, but we can assign numbers to them. Harkens back to that idea of checking the code book. If somebody says, I voted Democrat in the last election, but the code there is 1, you wouldn't know that without looking at the code book. Next, we have socioeconomic status. We can attach 1 to working, 2 to middle, 3 to upper middle, 4 to the 1%. Again, I talked about the concept of the code book. It's a document that lists the assignments of codes to the attributes composing these variables, meaning that it lists out the various codes and those code labels. So here we have an example. The variable name is AGR1. That means if we looked in an Excel spreadsheet, we'd have observations on the rows, so every person or every case is on the rows, but the variables are on the column. So it would say ID as one variable. The second column would be EXT1. The next column would be AGR1. And AGR1 stands for, I see myself as critical, quarrelsome, right? So these are questions that are being asked of the participant, and they have to say, do I agree or disagree to this statement? And it's not just agree or disagree. They have the option to select the various attributes that could exist in the variable AGR1. They can get a 1. They could select, I strongly agree with that statement. I agree, slightly agree, I'm neutral on that statement. I slightly disagree, and strongly disagree. So higher scores on this variable indicate more disagreement. So if you went there and row 17, meaning observation number 17, has the number 5 for the AGR variable. What that means is when they were asked to respond to agreement or disagreement to the statement, I see myself as critical, they say, well, I strongly or slightly disagree with that statement because I give a 5. This is very important for us to figure out what's going on in a data set, especially if you're working with secondary data from a website, a government-owned website, or Pew Research Center, various research firms. You need the code book to tell you what exactly is going on in the data set. Here's another example of a code book. We have a variable from the GSS. The GSS is the General Social Survey. It's been administered every few years with various questions from 1972 to about 2018, I think was the most recent one. Here are 2 variables from that data set. It's called poll views and attend. So the poll views variable says we hear a lot of talk about liberals and conservatives. I'm going to show you a 7-point scale in which the political views that people might hold are ranged from extremely liberal, 0.1, to extremely conservative, 0.7. Where would you place yourself on this scale? So poll views is basically asking them, do you identify as extremely liberal, liberal, slightly liberal, moderate, all the way through extremely conservative? And then you see 8 and 9, which are don't know and no answer. Same thing for how often do you attend religious services, the attend variable. So in your code book, it was going to give you the text of that question. It'll say poll views is the variable name. Question text will be listed. The options or attributes that could possibly be selected are listed there. Oftentimes it's going to say 1 to 7, like it says here, 1 to 7, but it's not going to say don't know. Here's another one. Here's the attend variable. So I take that from the last slide and I just highlight the various attributes. We have attend listed here. That's the abbreviated variable name. We have how often do you attend religious services? That's the definition of the variable. We have variable attributes, 0, never, less than once a year, about once or twice a year, all the way up to don't know and no answer. Here, we've attached numerical labels to these attributes. So if I ask somebody, I gave them the attend variable, and I asked them how often do you attend religious services, and I see in the data set that for the attend variable they have 7 listed there. Does that mean they went 7 times, or 7 times a week, or 7 times a year? No, what that means is, let's look at the numerical label for the variable attributes. We see that 7 indicates every week. So it's not several times a week, it's every week. Levels of measurement, these are very important. So levels of measurement are how we can assign numbers to variables. We have 3 of them: nominal, ordinal, and interval ratio. Nominal variables have attributes that just classify but cannot be ranked. These attributes only have the characteristics of exhaustiveness and mutual exclusiveness. So something like religious affiliation, college major, hair color, birthplace, political affiliation. While we can assign numbers to them like we did for political affiliation, we know that these only have attributes that can be classified but not rank ordered. So something like political affiliation, where you say, I'm a Democrat, I'm a Republican, I'm independent, I'm other, I'm green. All these things, they are categories, they're attributes that people can select, but you can't rank order them. You can't say Republican ranks higher than independent, ranks higher than other, right? There's no numerical association, right? You can't rank order them. You may subjectively like to rank order them, but there's no inherent rank orderedness to those categories. Next, we have ordinal variables. Ordinal variables are those that classify but can be logically rank ordered. Ordinal, ordered, right? So nominal, all you can do is say, I belong to this category or the other one. One's not better than the other. Ordinal variables can be rank ordered. So something like socioeconomic status. You can be upper class, you can be middle class, you can be lower class. If somebody says, I'm middle class, you know that you're higher than working class or lower class. If somebody says, I'm upper class or the 1%, you know that they are higher than middle class. So you can rank order. But the important part is that ordinal variables lack an associated numerical value. While we may say working class is number 1 and middle class is 2, upper class is 3, those numbers don't really mean anything. Does it just take one step to get to middle class and one step to get to upper class? Socioeconomic status is based on, education, occupation, income, social network, social capital. All of these things matter. So it's hard to associate a numerical value with this variable. You can't say if I make $10,000 more, I'm going to be in the middle class. Does it only take 10,000 more beyond that to get to upper class? So although we may have numbers attached to them, there's no inherent associated numerical value. All we know is we can order them. And then finally, interval ratio variables. These classify, they can be rank ordered, and they actually have an equal numerical distance between them. So one step below is one less. One step above is one higher, one more. And the distance between these attributes have meaning, right? So a good example is temperature. We know that if somebody says, I live in Phoenix and it's 75 degrees right now, and somebody says, I live in San Diego and it's 76 degrees here, we know that 76 is higher than 75. And we know that San Diego at 76 is exactly 1 degree Fahrenheit more than Phoenix. Again, nominal, they don't have numbers, they can't be rank ordered. Ordinal are just like nominal variables, but they have the added benefit of I can rank order them. And then interval ratio variables are the most sophisticated in that they have the characteristics of nominal and that they classify into groups. And they classify into groups that can be rank ordered, so they meet the criteria of ordinal. And why is that? Because they have numbers attached to them. So if we look at our earlier examples, we can break down into various types of variables. Sex here is a nominal variable, even though we have numbers attached to it. That's because they're categories. One's not better than the other. Same for political affiliation. Socioeconomic status here is ordinal. We can rank order, but we don't know the distance between working and middle, and between middle and upper middle, and between upper middle and the 1% aren't the same. You might even say that the distance between upper middle and the 1% is much larger than the distance between working and middle. And then finally, we have interval ratio. It has the characteristics of grouping, classification, categorization. If I'm 1, I'm in the 1 group. If I'm 2, I'm in the 2 group. If I'm 3, I'm in the 3 group. We know we can rank order because 3 is higher than 2 is higher than 1. And each step means 1 year. Exhaustiveness and mutual exclusivity. These are important characteristics to take into account when you're dealing with quantitative data or you're collecting quantitative data. Exhaustiveness just means that we're ensuring that all possible units can fall into a category. So we want to be able to handle missing responses. We want to provide the ability for everyone to identify as one category. For example, if we were looking at political affiliation, if we only said Democrat, Republican, Independent, that wouldn't be an exhaustive list of attributes. What about people who identify as peace and freedom? What if somebody identifies as green? By listing only Republican, Democrat, and Independent, you're leaving out other options that people could potentially select. It's always very good to include an other option. Make sure all options exist. You want to exhaust all possible options. And then something that's mutually exclusive means that each unit, each person, each participant, each observation can only fall into one category. So you don't want somebody to be able to identify as both a Republican and a Democrat. You don't want them to be able to identify as 18 and 22. So exhaustive, give them all possible options. And if you can't list all possible options, give them an other option. And then mutually exclusive means make sure that they can only identify as one of those possible options. I will make a note. We know that people identify as biracial, multiracial, multi-ethnic. So to say you should only identify as one is completely incorrect. Oftentimes you'll find on things like the census, you'll see instead of select the race that you most identify with, it's select one that you most identify with plus select all others that you identify with. Data entry, very important. and data analysis is also very important. So data entry, oftentimes when it's quantitative data, you're going to get things in an Excel format or a CSV, comma, separated values format. Just a very easy format for reading into data analysis software. So the CSV is a universal method of data entry. If you're going out and doing a survey and you collect the data from those surveys and you're like writing down what person number one said for this question, that question, it's wise to just input those into Excel or a spreadsheet of some kind, whether that's Google Sheets or Excel, and then you download those as a CSV because it's a very lightweight version of those data. Data analysis in quantitative methods, you may have heard of SPSS. It's very easy, point and click. The difficulty with SPSS is that it's expensive. If you don't have a site license through a university, then you're going to be paying hundreds of dollars per year for one license for yourself, and then you'd have to renew that every year. You can only work with one data set at a time, so one CSV at a time. Stata is another package that people like to use. Stata is more powerful than SPSS. It can do a lot of things, but now you can only work with two data sets at the same time. SAS is another old school program. I know people at the census use SAS still, very much command line oriented. You could spend hours trying to clean up your code. And then finally is R. So whereas Stata, SPSS, and SAS are expensive and can only do certain things and can only work with 1 to 2 to maybe 3 data sets at a time, R is open source, meaning it's free, meaning there's a community working to improve and develop components within R. Because it's object-oriented programming, you could work with multiple different objects or data sets. So instead of reading in one CSV file or 2 CSV files or 3 of them, you could have hundreds, if not thousands, of CSV files. Types of methods. So we have univariate statistics. We're just describing what's going on in a data set. Bivariate statistics, right? We're looking at relationships between two variables, variable. And then multivariate statistics, we're looking at multiple variables and their relationships with one another. Univariate statistics really focuses on describing a single variable at a time. Univariate statistics really focus on 3 main things. We have measures of central tendency, which is mean, median, mode. Measures of dispersion are also known as measures of variability. This is range, variance, and standard deviation. And then we have frequency distributions and graphs. So measures of central tendency, briefly, we know that the mode is the most frequently observed value or attribute. We can calculate the mode or the most frequently occurring category for all variable types, meaning we can calculate the mode for nominal, ordinal, and interval ratio variables. The median is the middlemost case. It's the 50th percentile, the point at which 50% fall above and 50% fall below that case, the middlemost point. The median is a little bit more sophisticated than the mode, and because of that, it requires a more sophisticated level of measurement. While the mode can be used for all 3 variable types, the median can only be calculated for ordinal variables and interval ratio variables. Can you calculate the middlemost case for political affiliation? Somebody says, I'm Democrat, I'm Republican, I'm independent, I'm other. What's the middle case? We don't know. Because we can't rank order them and say this one comes first, then we don't know what the middle is. However, if we had something like socioeconomic status, we say, because we can rank order them, we can figure out which person falls at the middlemost case. Then finally, the mean. The mean is also known as the distribution's average. The mean is computed by summing up the values of several observations and then dividing that by the number of observations. Because it's the most sophisticated measure of central tendency, it requires that we use the most sophisticated level of measurement, which is interval ratio variables. We can only calculate the mean if we have variables that have numbers attached to them, numbers that mean something. Here's an example. We can calculate the mode for something like age. We can see which category has the most number of people. We can also calculate the median, the middlemost point. We can also calculate the mean. Next, we have measures of dispersion or measures of variability. You can only calculate measures of variability for interval ratio variables. So we want to be most sophisticated when we're describing what's going on with one variable. We can use the mean, the median, or mode, but the mean is most sophisticated, so we want to stick with the mean. Beyond the mean, we want to get measures of spread. What I mean by that is, are most cases very close to that mean? Or are they more spread out, further away from the mean? Why do we need to know that? One example is mean temperature across a year for 2 cities. We look at the mean for Phoenix, we look at the mean for Honolulu, Hawaii. They both are 75 degrees. We also know that in Phoenix it gets much hotter and it also gets much colder. The winter could be very cold in Phoenix, but the summers are very, very hot. Whereas in Honolulu, the temperature is more temperate. It's very close to whatever that mean is. So while in Phoenix it gets very cold in the winter sometimes and it can get very hot in the summer, Year round in Honolulu, it's generally around 70 to 80 degrees. So the spread is much smaller in Honolulu than it is in Phoenix. And because of that, we need measures of spread. We can have two distributions with the same mean, but those distributions could look drastically different. So we say, let's look at the range. We know what the range is. The range looks at the distance between the highest number and the lowest number. The problem is, when we look at the highest number minus the lowest number, or the range, that number is going to be sensitive to extremes. If we look at something like somebody's income, there are people on the low end of the distribution, people on the high end of the distribution. However, that one person making $160 billion a year, they are far out from everybody else. So if we calculate the range, that range is going to be huge. It's sensitive to extremes. It's sensitive to outliers. So 0 and 160 billion are extreme outliers. So what do? Instead of looking towards the tails of the distribution, the ends of the distribution, and subtracting them, we can calculate what we call variance and standard deviation. So we can look inward and we say, where's the mean, and are these scores clustered or really close to the mean, or are they further away from the mean? So the mean becomes our starting point, not the tails, not the extremes. So variance is a measure of dispersion around the mean, but it's in squared units. And then the thing that we usually want is standard deviation. It's a number of units around the mean that cases fall. So the standard deviation helps us break up a distribution. Instead of looking at the high end and the low end, we say, where's the mean, and can we take steps outside the mean? One step to the right of the mean, one step to the left of the mean. And then we split a distribution into 3 steps above and 3 steps below. Variance you can think of as just a step towards standard deviation. Standard deviation is the gold standard here. So why do we use standard deviation? Well, it gives us a measure of clustering around the mean, so how close or how far most cases are from the mean. For example, we have this. We have amateur golfer scores and professional golfer scores. Amateur golfer scores mean of 100, professional golfer score of 70, right? So we see that the total score is lower for professional golfers, meaning they're doing better, whereas it's larger for amateur golfers, meaning they're doing worse. We also see we can take standard deviations and say, if we know that there's a distribution and we have a mean, each one of these distributions can be broken up into 3 steps, right? 1 step above, 2 steps above, 3 steps above, 1 step below, 2 steps, 3 steps below. 1 step below to 1 step above the mean is going to constitute 68% of the cases. -1 and +1 standard deviations of the mean also covers 68% of the cases, regardless of the mean of the distribution. So the standard deviation is very helpful for describing what's going on in a distribution. Then we have graphing. We can calculate a frequency distribution. Frequency distribution say how many people said this. So I think this is the attend variable from earlier. 1,132 people said, I go to church once a year. It gives you percentages of people said that. That is a frequency distribution in table form. We have a pie chart. Each slice represents a percentage of the total. And then we have bar graphs. We have a special case of bar charts called histograms. Bar charts are usually not supposed to be touching, but if they are interval ratio variables, 1 step equals the same interval above or below. When we have that, we have a special case of a bar chart called a histogram. Bivariate statistics. So this is where we're moving away from univariate statistics or just describing what's going on to bivariate statistics that help us examine relationships between 2 variables. Bivariate, 2 variables. We're getting away from descriptive statistics into inferential statistics, explaining something about the social world, generalizing to the social world. All right, bivariate statistics is an analysis of 2 variables simultaneously for the purpose of determining an empirical relationship between them. We want to generalize. In univariate statistics, we're describing just one variable, not how it's affected by or predicts or results from another variable. But when we start thinking about research questions about the social world, we need to start thinking about 2 variables at the same time and how they're related to one another. How's this X variable related to this Y variable? And we have 4 different bivariate tests. There are many more, but these are the 4 main bivariate tests. We have chi-square, not chi. Do not say chi-square. It is chi-square, the Greek letter X, chi. We have the t-test. So the chi-square is a measure of association. The t-test is a measure of mean differences between groups. You're looking at the mean for one group and seeing if it's different from or the same as the mean for another group. So we're looking at the relationship between group membership and their overall score or their means. The analysis of variance, or ANOVA, is similar to the t-test. It's actually an outgrowth of the t-test. The t-test, again, looks at group membership, so group 1 and group 2, and whether or not the mean of group 1 is equal to or different from the mean of group 2. The analysis of variance says, well, sometimes we don't have just 2 groups. Sometimes we have 3, 4, 5, 15, 30 groups. And we want to see, does the mean of this group, group 1, is it the same as or different from all the other groups? That's what the analysis of variance does. So it looks at group membership for 3 or more groups and how their means are similar or different. Then finally, we have correlation. Correlation is the measure of relationship or association between 2 variables, but it's looking at interval ratio variables. Does one influence or increase or decrease the effect of others? This will come in handy once you get to the next stats class. It'll help you figure out which kind of bivariate tests are going to be most important for answering your research questions. Here I've broken it down by the type of variable and whether or not it's an independent variable or a dependent variable. So here we see we have a nominal independent variable, interval ratio, independent variable. We have nominal ordinal dependent variable, interval ratio, dependent variable. So if we have a nominal or ordinal dependent variable, so that's going to be our y variable, and a nominal or ordinal independent variable, our x variable, we should use a chi-square test. If we have an interval ratio y variable, dependent variable, and a nominal ordinal independent variable, so an x variable, then we use a t-test or an ANOVA. So this is basically the group to which someone belongs, right? You are either Democrat or Republican or independent. And then you have a dependent variable that is interval ratio, something like IQ score that has numbers attached to it. We could use a t-test or an ANOVA. We could say, does the mean IQ score differ by political affiliation? So do Democrats have higher or lower IQ scores than Republicans? Or do Democrats have higher or lower scores than Republicans or independents or others? The important thing to remember here is, again, the t-test looks at mean differences for 2 groups only, whereas ANOVA looks at mean differences for 3 or more groups. And then finally, I have correlation, which is dependent variable that's interval ratio, and an independent variable that's also interval ratio. So let's say education and income. Education being years of education, interval ratio, year 1 year, 2 year, 3 year, 4 year, 5 year, 30 year. And income, $1, $2, $3, $4, $5. We can look at a correlation to see, is there an effect of education on income? Here we have an interval ratio measure that's independent and a nominal ordinal dependent variable. That's not really a test in bivariate statistics. You might even start thinking about logistic regression here, but that's the next phase where we're moving on from bivariate tests to multivariate tests. And then finally, multivariate statistics. So we're examining relationships between 3 or more variables for the purpose of inference. So univariate statistics, it's just describing, whereas bivariate and multivariate statistics are really looking to infer or generalize to the population. The difference between bivariate and multivariate statistics isn't just that we're adding one variable, but we're trying to reach that idea of causal relationships. The 3 criteria for causality in social sciences at its base level are an association, time ordering, and the absence of spuriousness. So it means association, there must be a bivariate relationship. X must relate to Y, so there's a correlation or a chi-square relationship or a t-test relationship or an ANOVA relationship. That's the first criterion. Second criterion is time ordering. The X variable must come before the Y variable. Group membership must come before IQ score. The final one is the absence of spuriousness. To make sure that spuriousness doesn't exist, we also have to throw in a 3rd variable and a 4th and a 5th. So multivariate statistics help us get closer to causality in social sciences. And there are multiple tests that analyze relationships simultaneously by looking at a bunch of different variables. You can have multiple independent variables with one dependent variable. So you have x1, x2, x3, x4, x5, x15, examining all their relationships with one another and all of their relationships with y. We have MANOVA, it's multivariate analysis of variance. RM ANOVA, which is repeated measures ANOVA, which is another type of ANOVA, but it's not really multivariate. The main thing we have for multivariate stats are regressions. Multiple linear or OLS regression. We have a binary logistic regression where the outcome is a yes, no, 0, 1. Multinomial logistic regression. Poisson regression, which is a count regression. Negative binomial regression, which is another count regression. Event history / survival analysis, and time series analysis. So event history meaning the time until an event happens or the rate of failure or success of an event. And then time series, a correlational look at how time affects relationships. And that is it.